Then Sunday night, they're like, oh, it's going to be ready at 4:30. So I go all the way from Kerrville all the way out there.
Oh, no.
And pick it up. And it's not ready. They didn't even look at it. I was like, I thought you said you needed. Well, we forgot to look at it. We forgot to look at it. So they're trying to call around for parts on a Sunday night, 6 o'clock on a Sunday, trying to find parts. I'm like, it's not going to happen.
Yeah.
So they gave us another round. I was like, great.
Customer service, man.
Yeah, I'm kidding.
All right. So here's what I had planned for today. What was planned was you were going to do a nice quiz today, right? I told you we were going to. And then what happened was I got Windows blue screen last night, and it has from about 4 o'clock yesterday to 2 a.m. I've been trying to recover my computer, and then I went to sleep from 2 to 5, and from 5 to 10 this morning I've been trying to get this thing fixed. Rushed into work to teach my 11 o'clock class, then to my office for 5-10 minutes. I didn't have enough time to make a quiz. I apologize because I like to keep my word, and I guess that means we'll just have to have it on Thursday. Okay, so I'm postponing the quiz till Thursday.
Is it going to be over this?
It was supposed to be today. And whatever we were supposed to do, we're going to have a quiz on Thursday. It'll be a longer quiz. We're going to take some time on it. It's going to be a good 15-20 minute quiz. Okay?
Wait, so
Yes.
It'll be based on?
It'll be based on all the rules of differentiation. And then let's see how today goes. Okay?
All the rules of differentiation? Like all of them?
Power rule, product rule, quotient rule, chain rule. Yep. So what did y'all think of chain rule? You got to go home and do your homework?
It wasn't really that bad.
No? You okay with it? It's all right?
Completely skipped method 2 though. Like I was like,
Yeah.
you started method 2 on the video, I was like, nah.
No? Yeah. Well, everyone kind of has to pick what works for them. You know, some people like the second method more than the first. Some people just go straight to the third method. It's up to you. So hopefully I provided you with enough framework for you to build up your own skills and kind of make it make sense to you in your own head. So, but today we start 2.7, right? 2.6, sorry, called Implicit Differentiation, and the video for this was only 6 minutes long. But I do want to kind of rehash whatever I talked about there. The important thing is that all the tangent lines we've been doing, all the derivatives have been, right, slope of tangent line, has always been on a function. It has always been on y equals some function of x. And anytime we deal with functions, y is some function of x, then it must pass, the graph must pass the vertical line test for us to be able to say that y is a function of x. And that means that if you plug an x value in, there should only be one output, one y value that comes out. And we call x here the independent variable. Independent meaning it can kind of be whatever it wants to be. It's independent. And the y is dependent, meaning that to determine y, it depends on the x, right? It depends on the x being plugged in. And that's been great. We've been able to find derivatives, no problem, right? And we've always said something like this, y prime, and we've understood that Leibniz would have said dy dx, right? We've written this down, we've used y prime a lot, right? But now we're going to start to lean more towards this notation. And you'll see the strength of that notation as we proceed. But keep in mind that this came from the idea of the slope of a line, rise over run. Do you all remember that? Rise over run. And then we said that this was kind of like change in y over change in x. Right? But if you take a real tiny, tiny little piece, then it becomes this differential, this infinitesimal change in y and this infinitesimal change in x. Right? We good? The key right now for you to understand is that, I don't have a marker other than black. Let me go grab one. The key is that if you look at dy over dx as a ratio, as a fraction, this change in x right here has always been constant. And what do I mean by that? It's kind of like when I draw this triangle in here, and I say this is dy, this side, change in y, and this is dx, we've always assumed that that dx is like 1, like a unit length. So if this is, let's say, 1 foot, then this right here, the change in y might be 1 foot, or it might be 2 feet, or it might be 3 feet. It depends on the function itself, right? How fast this is changing depends on how fast that's changing, but the rate that that's changing has always been the same. 1 unit per time. Does that kind of make sense? All right, so when I start saying this now, what I'm going to be saying is we are looking at the derivative of y with respect to x. With respect to x. When I say with respect to x, I mean that x is independent and changing at a constant rate. The reason why I have to point that out is because we are going to move away from that in a little while, and we're going to have different things down here. Sometimes it'll be dx, it might even be dy, it might even be something else like some other variable, dt. So stay tuned, all right, it's coming, but I want to be clear on what we meant by this as we proceed. All right, so tangent line, we needed a function of x, but what about that curve? Right, so this section is about, well, that's still a curve, right? It still has very clear tangent lines all over it, right? It's got tangent lines all over it, but it's not a function, right? It fails the vertical line test. So is there still a way for me to find the slope of this blue line?
Yes.
Yeah, there's got to be a way, right? I mean, it exists. We should be able to find it. The problem is, though, if we plug in some value of x, let's just say we plug in a single value of x and try and treat x as being independent, your output has 2 values, right? You're going to have one y value up here and you're going to have another y value down here. And if I put that other y value down there, now you have a second tangent line. Oops, I missed that pretty good, didn't I? Good enough. All right. So if I try and treat this like y is depending on x, it not being a function means that we're going to have 2 different tangent lines, right? Because there are 2 different points on the curve. So how are we going to get around that? And not only how are we going to get around it, what is our derivative going to look like? All of our derivatives up to this point have always been functions of x. Yes?
Would you just limit what you're trying to find as far as the above or below?
You could like try and cut this curve up and say, let's just look at the top half of the circle. You could do that and then look at the bottom half. The problem is that if you get something more complicated like this, that's not a function of x either. That fails the vertical line test. And it will be much more challenging to cut it somewhere where you can just look at a top and a bottom part. So do we have a way of doing it? Yes, it's called implicit differentiation. All right, y'all with me on the idea, the concept? So how can we tell when we are looking at something that we would need to use implicit differentiation for versus something we would not need implicit differentiation for? And I gave some examples up here. These first 3 examples, y equals 3x plus 1, y equals root sine x, x equals y cubed plus y. All 3 of those are what we call explicit equations. That means that you can solve for one of the variables very explicitly. I know what y is explicitly. You give me an x, I give you a y. Very simple, right? You give me an x, I give you a y. Now this one's different. This one says you give me a y, I give you an x, right? But it's still an independent variable, which is here the y. The dependent variable is x. Independent variable here is x. Dependent is y. Independent here is x. Dependent is y, right? Compare those equations, because these are equations. Compare those to these. If you give me an x here, I can't give you a y directly. I have to actually go solve for y, right? I'd have to go solve it. And if I try and solve this one for y, how could I do that? Tell me how I could solve this one for y. You can move the x over.
Take the square root with plus or minus,
Okay, I can take the square root on both sides. And when I do that, I have to do plus or minus.
because you initiated the root.
Because we initiate the root, that means you have to do the plus or minus. Good job, you remember that.
So 4 minus x.
So this is no longer one function. This is now two functions, isn't it? It's y equals positive root 16 minus x squared and y equals negative root 16 minus x squared. And if you were to graph this, it would draw the top half of the circle. And if you were to graph this, it would draw the bottom half of the circle. That's how that would work. So we could on that first one, try and turn it into explicit. But in doing so, we would generate two functions out of one. That's how we could get around the problem. Understand that? Could you take the derivative of that right now?
Yeah.
Sure, right? Chain rule? Okay. In this one, same, you could do chain rule.
Isn't that the slope though?
Is what the slope?
That.
No, this is just a function. This just draws the curve.
Oh yeah.
This just draws the circle. That's all it does. All right, so that was kind of me presenting you with an implicit equation saying, look, it's hard to get y by itself. But then I was saying, yeah, but we could do it. It just generates two curves instead of one. This next example, x cubed plus cosine y equals x plus y squared. You can't solve for x, and you can't solve for y. You can't solve for either one of them. No matter how hard you try. It's never going to happen.
Just because the y is in the argument.
That's right, because this y is trapped right here in the cosine. You will not be able to release it from the cosine unless you initiate an inverse cosine, right? Inverse cosine undoes cosine. But as soon as you initiate an inverse cosine, you're going to trap the y that's over here on the other side inside of an inverse cosine. Let me show you. So let me try and solve for y. I get cosine y. I'm going to move this term to the other side. X plus y squared minus x cubed, right? And then let me try and get that y to be released from cosine. So I come in here with the arc cosine or cosine inverse. What you do to one side, you must do to the other, right? So cosine inverse on this side, and then of all this junk in here. So this side's y, but this side over here also has y in it. So that's a circular argument. In order to know y, I must know y, right? To know y, I must know y, and I can't ever know y unless I know y. So you see, I mean, I cannot get y solved for explicitly. But if you actually go and try and plug in different values of x and y, you can satisfy this equation. There are x's and y's that will satisfy this equation, and if you look at all of them, it will draw a curve. And the question becomes, can we find tangent lines on that curve? Yes, we should be able to with today's information, the technique of implicit differentiation. All right, and then the last one is just another example of one that you can't ever get x by itself or y by itself. It's just, they're just trapped and you can't ever free them. So do you see the contrast between the two types of equations? The ones that we've been doing versus the ones we're going to try and do today. Oops. So look at this equation right here, x squared plus xy minus y squared equals 4. In the video, I told you I would actually show you how you could solve that for y. Yeah, I think I'm going to hold off on it though, just timing-wise. We have 2 days on our schedule to cover this topic. If I have time, I'll go back and show you how to solve this for y. It's more just to show you a cool technique. It's not going to be useful for anything we're going to do in here right now. So I think we would all kind of look at that and say, yeah, that's not easy to solve for y. And if you try on your own, you'd see why. All right, you ready? Okay. Whoa. So I'm gonna start working with these examples. And I'm going to start with the x squared plus y squared equals 16, that circle. I want to find dy dx. That means I would like to know the rate at which y changes. I want to know how fast y changes with respect to x, left and right, right? And I'm assuming here that my left and right change is happening in a unit time sort of manner, right? It's increasing, let's say, that's unit length.
So y equals mx plus b, basically.
What is that?
That's what we're trying to find.
We're trying to find the m in y equals mx plus b. We're trying to find the slope of the line. All right, well, I can't solve that for y easily, so what's the technique? Well, this is the implicit differentiation. Implicit differentiation. I'm just going to put that, implicit diff. So here's how it works. We're going to write the equation down, and we're going to take the derivative on both sides of the equation. And we're going to take the derivative with respect to x. And the reason we're doing that is because that's what this means, with respect to x. So the way I'll write that is I'm going to take the derivative with respect to x of the left side. And then I'm going to take the derivative with respect to x of the right side. And if you go back in the notes, when I was talking about notations, there was a notation that looked like this. It said that y prime, you could write it as d dx y, like that, like this. This means take the derivative with respect to x of whatever's here. That right there would mean the derivative of that y. So do you see I'm saying take the derivative with respect to x of this side equals derivative with respect to x of that side. Yes?
This is why you like Leibniz notation.
Yeah, especially the next section we're going to do, 2.7. Leibniz notation is perfect for that section. And actually, the Newton's notation is really clumsy and dangerous in that section. Okay, so I'm going to take derivative on the left side. When I take the derivative of a sum, I can take the derivative of each one separately, can't I? Okay, so let me do that. I'm going to just write it down. Take the derivative with respect to x of the first term plus the derivative with respect to x of the second term, and that must equal the derivative with respect to x of the constant over there on the right side, 16. Now on this right here, this first one, this is very natural. It's what you expect it to be. The derivative of x squared should be what? 2x. And the reason is because we're differentiating with respect to x. And so it's just the natural derivative, everything we've learned, right? 2x. No problems there. This second term is where we have to be careful. So remember, chain rule was like an onion, right? We started with the outside and we worked our way in. Since this y here, this has y and it doesn't have x, when we do the derivative on this, we have to do the chain rule. So what is the outside layer to this right here? Squared, right? So what is the derivative of something that's being squared? 2 times that something, right? So let me write that down first. 2 times the something to the first power, right? I don't need to put the 1, but that would be the derivative of y squared so far. But then chain rule says we go inside, right? Inside would mean the next function inside, which is just y by itself. And I have to take derivative of that too. And what is the derivative of y with respect to x?
Y.
It's exactly what I just said. What is the derivative of y with respect to x? It is the derivative of y with respect to x, right? That is actually what we're trying to find. Do you see that? What we're trying to find just appeared in front of our eyes. See it? I don't know what it is, but there it is.
So you just
Just leave it like that. Just,
you know what?
I'm not going to write as y prime, I'm just going to leave it just like that. Do y'all see that as chain rule? If you have a box being squared, and I want the derivative. Last class we said it would be 2 times that box to the first power times the derivative of that box. Sorry, that's a derivative, that's first power, right? So the 2 comes out, then you write the box, then to the first power, and then times, chain rule, the derivative of what's inside. Derivative of y is, with respect to x, is the derivative of y with respect to x. Now, do y'all see that we actually did do that here? We did that. The 2 came out, right? 2x to the first power times the derivative of what's in there. What's the derivative of x with respect to x? What's the derivative of x with respect to x? That's a 1, isn't it? But I don't need to write it. You could if you want, but we don't need to. Y'all need to tell me if y'all are clear on this or not, or if y'all need any clarification.
And that's your answer.
Now, we're not done, because it's an equation we have to keep working.
So it's all like a hidden 1.
This one is.
Yeah.
Yeah, it's there. Yeah.
How relevant is that?
What's that?
How relevant is that hidden one later?
How relevant is that? That's a 1? Not relevant at all?
Okay.
Unless we're differentiating this equation with respect to a third variable, which we will do next. Well, I'll do it today, just so you can see the contrast, all right? All right, so now I have an equal sign, right? Because I finished up the chain rule there. Done with the derivative of that. Equals, what's the derivative of a constant?
0.
That's not going to ever change, okay? Derivative of a constant will always be 0. And there we go. What were we trying to solve for? I'm going to put this back to a 1. Just, it's not there.
We're trying to solve dy.
I want to know what dy dx is, right? And you have an equation right there that has dy dx in it. So it's your job now to isolate that. Get it by itself on one side of the equation, which should be pretty easy to do. Let's just move this term to the other side, so subtract it. Like that, right?
And then divide the 2y.
Divide out 2y. And clean that up a little bit. What is that? Just negative x over y. That's it. That's your derivative. Now that should look weird to you in some way because, like I said before, every derivative we've ever taken before, we started out with a function of x, right? So it had just x's in it. And when we took the derivative, our answer had x's in it. Yes? This, our derivative has not only x's in it, but y's. Does it make sense to you that our derivative should have both x's and y's?
Yes.
Yes, hopefully, yeah. Why does that make sense to you? Because it's a circle, if I pick an x value, that's not enough for me to know what the slope of the tangent line is. I must also provide you with the y value. I'll give you the x value and the y value, then the derivative can be computed. So if I give you this x value and this y value, then you can tell me it's that point. This would represent the slope of the tangent line there. If you give me that same x value and a different y value, the one that corresponds to that point, it will give you that one. You see that? So somehow the derivative already knows it needs both x and y to do this. So let's go to our circle. Bless you. Let's see if it actually works. This equation is the equation of a circle with radius 4. What is this point right here at the top? What's the point? 0, 4. The x is 0, the y is 4, correct? Let's try that. Let's plug in for x, let's plug in 0, and y, let's plug in 4. And what would you get? You get negative 0 over 4. That's 0, right? Do you agree that at that point, the slope of the tangent line is 0? Yes. So that actually does work. How about this point down here? That's 0, negative 4. And I'm going to get the same answer, right? Slope of that tangent line would also be 0. How about, I know you want to do these points next, right? I avoided them on purpose. Because this is the point 4, 0, and what's wrong there?
We have a 0.
Yeah, now you're going to have division by 0, which is telling you that there's something wrong with the slope of the tangent line there. It's a vertical line, and vertical lines don't have slopes. Their slopes are undefined. But you can see it though, right? That right there, that slope doesn't exist. And neither does the derivative. It doesn't exist there. And if you try negative 4, 0, same thing's going to happen. How about right here? Do you all know what point that is?
2.
No.
2 and 2.
No, not 2, 2. It's not 2, 2. What is that?
It's some trig coordinates.
It is some trig coordinates. Let me see. Maybe we can get it.
It's square root of 2.
Maybe we can do it. Yeah, it's related to that. It's related to that. How about I do this? I can do this 2 ways. I can actually go find them for you, or I can change the entire problem and make it easier. What do y'all want to do? Let's change the entire problem, make it easier. Watch how I could make this easier. What if I made that a 1?
Well, yeah.
Would that have changed this derivative?
No.
Why? Because the right side was a constant, right? And the derivative was 0, and it wouldn't have mattered if that was 1 or 16, right? Wouldn't have mattered? And that changes this to a 1. And now we're on the unit circle, right?
That's 2 square root of 2.
And now you know that that's what? This coordinate is root 2 over 2, root 2 over 2, right? That's what that is. So what would happen if you plugged in this and this, x and y, right here?
Would be a negative.
You'd get negative 1, wouldn't you? And does that make sense that that's the tangent line there?
Yes.
Negative 1. It's pretty amazing that this works, but it does. I can go anywhere on this circle. As long as you give me a point, I can tell you the slope of the tangent line. Anywhere on the circle. But you have to give me the point, x and y, then I'll provide you with the tangent line. That's pretty cool.
You won't have to find a point. You will have a point given to us.
It's going to be the same thing it's been in the past. Find the slope of the tangent, or find the derivative, or it might say find the slope of tangent line at this point.
Okay.
Yeah. So everything we've done has been either find the derivative, or find the slope of the tangent line, or find the equation of the tangent line, right? That's the 3 things. Those are all still fair game. It's just a matter of what's your derivative, how are you getting that derivative now? Yes?
Do you recommend memorizing this x squared?
The relationship with a circle?
Will it come up?
I don't know. Maybe. You can. I think what's more powerful is if you think of it this way. Isn't the x-coordinate on a circle the same as, like if someone gives you a circle and they give you a radius of r and an angle of theta, isn't this point r cosine theta, r sine theta? Yes? Yeah? And isn't the x divided by the y, if I take that, take the negative x and divide it by the y, the r's cancel and I get negative, which is negative cotangent. Isn't this negative cotangent? Negative cotangent of theta. What I'm trying to get you to see is that if you graph negative cotangent theta, it actually graphs your tangent lines. Because, right, like cotangent has asymptotes. Those asymptotes are when your angle hits here or when your angle hits here. And remember, you can keep going theta all around. So you'll keep on getting those over and over and over. When you start to see like the underlying stuff, like how things are connected, it's almost scary how it's connected. It's just so intertwined. But okay, we're going to move on.
Professor.
Yes.
Let's say, for instance, if we had shifted that circle and we weren't able to tell that, let's say, that particular point was a vertical line.
Uh-huh.
Would you have to try and approach it really close and see what it's doing? Or?
Well, if you shift it, I can write the equation. I can change the equation for a shift.
Right.
So like the equation, the general equation of a circle. This is the general equation for a circle that has a center of hk. So if your center is 0, 0, then this just becomes x squared plus y squared equals r squared. But if you want to move it around, then you just adjust your h and your k. So let's say that I adjusted h and k, and I did this. Okay, so now I've moved it, right? The only thing that's going to change is when I take the derivative, right, implicitly. When you take derivative here, you're going to have to use chain rule. The 2 is going to come out, right? Here, the 2 is going to come out. And in that derivative, it's going to account for the shift. Does that answer your question, Gunnar? Okay. All right, let's look at the other problem. X cubed cosine y equals x plus y squared. Let me write it down first before I erase it. X cubed plus cosine y equals x plus y squared. Now, I don't remember when I made these notes if I had made that problem up. So, okay, I was going to say if that's Windows coming up, giving me some prompt. Enjoy the new features. All right, so I'm going to try and get this thing to graph this for me, because I want you to appreciate the ugliness of this if it is ugly. Let's see, we have x cubed plus cosine of y equals x plus y squared. I'm hoping this graphs. Yeah. There we go. That's definitely cool looking, right?
Weird.
And it's definitely not a function of x, right? So we should be able to find slopes of tangent lines. It's just a matter of that we can't do it using our normal derivative. We have to use implicit differentiation. So let's go for it. I'm going to take the derivative with respect to x of the left side. And then I'm going to say equals the derivative with respect to x of the right side. I have 2 terms on the left, right? So I can split it up. Don't need product. Just some difference, right? Separately. On the right side, I can split that, right? And kind of the rule of thumb here is if you're taking the derivative with respect to x of something that just has x's in it, then you just do it like we did before. Derivative of x cubed, 3x squared. So there's nothing new there. It's when you have something other than x, or even possibly x's and y's mixed together, you have to be careful. Here I just have cosine y. Well, I know that the derivative of cosine of y should be negative sine y, right? But the chain rule says I would then need to go inside the cosine, take derivative of what's in there. And derivative of what's in there would be dy dx. So the way I'm going to write this is plus, I guess I'll write negative sine y, right? That's derivative of cosine of y. Chain rule times dy dx. Am I done on the left side? Nobody has a question? Like, hey, where did that dy dx come from? No? Yes? It's the same thing as we did before. You know, if I say, what's the derivative of cosine of my hand, right? It was negative sine of my hand. Then you would uncover this and say derivative of what's in here. But what's in here is actually y, so the derivative of y is dy dx. So this was negative sine of my hand times derivative of my hand. Does that make it more clear? Equals, what's derivative of x? 1. Plus 2y, so it's pretty normal up to that point, but then because it's y and you're differentiating with respect to x, you have to take derivative of what's in there, which is the y, so dy dx. So your dy dx appeared twice, yes?
Is that ultimately the derivative of whatever yx divided by whatever x is?
No, it's not. It's the whole thing together means the derivative. They're not individual derivatives. The top by itself is what we call a differential. And so you have the ratio of these two differentials. The differential this is the infinitesimal change in y divided by the infinitesimal change in x. That ratio is a slope. The slope is called the derivative. Each one of these by themselves are not derivatives in that sense. To have a derivative, you must have one variable dependent upon another. You can't look at the derivative of a variable by itself. All right. Yeah, this is a little different, right? I don't like that parentheses. Let me just rewrite this. 3x squared minus sine y times dy dx. And my goal is to try now and isolate dy dx. Right? Because I want the answer. I want my answer. Dy dx equals something. And right now I have dy dx on both sides of the equation. So what we're going to do is we're going to move all our dy dx's to one side, anything that does not have dy dx to the other side. And it doesn't matter which side you go to. All right? It's your call. So I'll make the call this time. I'm going to move this entire factor. I'm going to move that entire thing to this side. The reason I'm doing it that way is because this is negative over here. And when I move it over to this side, it's going to become plus, right? So I'll have all my dy dx's on this side. But I also have a 1 here. And 1 doesn't have a dy dx, so I'm going to pop that to the other side. Subtract it on both sides. So I will have this. You just tell me if you agree. 3x squared. The 1 from the other side is going to come over and join. On the right side, I had 2y dy dx. And then I also took this whole thing and moved it to the other side. It became plus sine y times dy dx. Yeah, and the reason we do this to get all the dy dx's is so you can do just a basic factoring technique from college algebra, greatest common factor, right? These both have a dy dx in them. So I just factor it out. So I have 3x squared minus 1 equals, I'm factoring out dy dx. I would be left with what? 2y plus sine y. And now to get the dy dx by itself, because this is multiplication, right? I'll just divide that entire thing on both sides. So take this, divide it by itself. Take this and divide it by that big ugly thing. And so you get dy dx equals 3x squared minus 1 over, we divided by 2y plus sine y. There it is. Y'all know what I did there? Dividing this big chunk on this side makes it go away. Dividing this by that big chunk makes it appear. So if I want to know the slope of the tangent line, right? I'm going to have to provide the person whoever wants the slope of the tangent line is going to have someone provide not only the x coordinate, but the y coordinate, right? You hand them the x and the y coordinate, then they will be able to produce the tangent line for you. Keep in mind though, like if someone just said, okay, cool, I would like to know, like, what's the slope of the tangent line at like the point 0, 1? You would plug in 0 and plug in 1, you get an answer, right? That is not necessarily correct, because in order to use the point 0, 1, 0, 1 must what? Be on the curve. So you have the points you plug in here must belong to the original curve. Remember we drew the curve, it looked like this thing? You can't pick some point over here and talk about the slope of the tangent line. You must have a point here. So you'd need to generate a point, and most of the time that will be given to you. They'll tell you, hey, find it at this point. That way you don't have to actually come up with it yourself.
How do you plug this in calculator?
What do you mean?
equation.
How do you plug it in? I don't know what you mean.
Like if I put it on a graphing calculator.
Oh, okay, good question. You can't.
Oh, cool.
Unless your graphing calculator has what's called implicit graphing. So look, this program that I use here, this WinPlot, when I say I want to put in a graph, I can put in an explicit function, which means like x sine x, right? It's a function of x, and it'll graph that for me. There it is. Or if it's not something I can solve for x, I can put it what's called implicit form, and that I just type in the equation, and it graphs it for me. So that's what I did up here. I typed that in as the equation, and it did its job. I do not believe the graphing calculators have that feature. They have function graphing, parametric graphing, polar graphing, and maybe something else, but they can't handle this.
What about the TR Day10?
As far as I know, cannot handle it either.
There's nowhere to plot a point.
This computer program is doing a bunch of guessing.
What X and Y could be.
Yep, X and Y's.
Which estimates is
Yep, it's a bunch of estimates within a certain tolerance. It just does it so fast that it looks like it knew what it was doing. It can guess a lot faster and plug in and check a lot faster than we can, right? Yeah, that's an interesting comment though, because if you graph that derivative up here, then how would that correspond to this graph? That's beyond the scope of this class. We won't touch that. That's interesting though. All right. Ready for another one? Cosine xy equals 1 minus sine y. Do y'all want to see it? Or just do the derivative? Do y'all want to see the graph, or no? You're okay? Maybe after. All right, so we take the derivative on both sides. The derivative with respect to x of cosine xy equals the derivative with respect to x of 1 minus the derivative with respect to x of sine of y. So I'm saving myself a little bit of time by recognizing that this is a difference of two things, so I'm going to do derivatives split up over there. Now the derivative of cosine xy, maybe let's save that. Let's do the right side first. What's the derivative of 1? 0. What's the derivative, and this is a minus, what's the derivative of sine of y with respect to x? Cosine y dy dx. Chain rule, right there.
Can you split the cosine x and cosine y and just have cosine x times cosine y?
No, that's not one of the formulas that we had from pre-cal, that you can take a product in a cosine and split it into two cosines. All right, so you ready for the left side? That's composition, right? This is chain rule. So I'm going to take derivative of cosine of my hand, right? What's the derivative of cosine of my hand? Negative sine of my hand, xy. Chain rule. Times the derivative of my hand, right? But my hand is a product. Do you see that? And that means that when I multiply here, I have to put the product rule in here for those two pieces. So I'm going to give myself some room, put some parentheses here. Product rule says derivative of the first one times the second one plus derivative of the second one times the first one, right? So I'm going to write it this way. The derivative with respect to x of the first one times the second one plus, I knew I was going to run out of room. Move this over a little bit. Plus the derivative of the with respect to x of the second one, which is y, times x. Do y'all see how that works?
But times dy dx, because you have one more inside the cosine.
No. We work from the outside in. Derivative cosine of something is negative sine of that something. Times, now go inside, right? What's the derivative of this? Well, it's a product rule, so it's derivative of the first one times the second one, plus derivative of the second one times the first one. And then I'm done. There's nowhere else to go. Let's do what's inside that parentheses. This is negative sine of xy, parentheses. What's the derivative of x with respect to x? 1 times y? Y. So that's just y, plus, what is the derivative of y with respect to x? Dy dx. Times x, close parentheses, equals negative cosine of y times dy dx. Any questions? Don't be afraid to ask.
So anytime there's a y, it's dy dx.
If you're differentiating with respect to x, if there's a y, yes. Now if it's y squared, you'll have 2y dy dx, right? And remember, if we're trying to solve for dy dx, then at some point we should get a dy dx, right? Like if you never have a dy dx pop out, you're never going to be able to solve for it. So something is wrong. All right, I'm done with the differentiation, right? So now I just need to get all my dy dx's on one side. Problem is, though, that this dy dx in here is trapped in that parenthesis. So I need to distribute that negative sine xy through to those two terms before I start to try and move things. So I'll do that. I'm going to distribute this to this and this to this. Now watch the way I write it, okay? I have negative sine xy times y. That y does not come in there and becomes y squared. It's just going to stick out front. So I'm going to write negative y sine xy. Then when I do negative sine xy times this stuff, same thing. This stuff doesn't go in there. It just goes in front of the sign. So minus, again, dy dx times x times sine of xy. Do you agree that I've distributed this through to both of these? And then equals the other side. Negative cosine of y times dy dx. Now I have allowed myself the freedom to move things around. So I think I'll take that one on the left, this dy dx factor right, or term right here, this whole thing, and take the whole thing and move it over to that side. So that'll be my next line. And since when I move that one over, it's going to be positive, I'm going to put it in front. That's just my preference, not required. Y'all still with me on that? Why did I do that? So I can factor out, right, a dy dx on the right side. So when I factor this out, it's going to come out, there will be a parentheses, and I got to figure out what's left, right? So I'm going to do a shortcut because I can cheat because I have markers and you don't. That's what would happen if you pull that out, right? And then you divide through by everything in that parentheses on both sides. And that will be your result.
Can you factor in sine xy?
I don't know, let's see. Let's see what we can do. It's that over x sine xy minus cosine y equals dy dx. I don't see that we can factor it out because I would need one here also to be able to factor it out and cancel. I can't cancel these though, no way. So that's it. It's ugly, but it is the slope of the tangent line at that point. If you want to know what it is, that's what it is. Did we want to see it or no? No? Draw it or?
Yeah.
No? Okay, what do you got?
Is it possible to do that backwards?
How do you mean?
Yeah, you have the like go backwards and go back to the original.
Yes, that's called Cal 2.
Why did I know you were going to say that?
Although that is a very difficult problem. That's something you would do more in Cal 3 because you have two variables in there. It requires what's called partial integration. It's a little more involved. In Cal 2, we spend all of our time working on functions of x. We don't get into things like this where they're not, we make sure in Cal 2 that everything passes the vertical line test. All right, so I don't remember what the original problem was. X cubed, is that right? No. Cosine of x times y, right? Equals 1 minus sine y? That was it? Seems so innocent. Oh, whoa. Oh, that's fantastic. I'm glad I graphed that. I'm glad that I graphed that. That is, now it kind of gave up. It only graphed in the window. It continues out. But look at that. There's some really cool stuff here. Because this curve is not like any curve that we would normally think. Like a circle, right? That's okay, circle. We see circles all the time. This has all sorts of things happening to it, right? Like if you wanted to know what was happening, let's say at x is 2, you might have what? One slope of a tangent line there, another slope of a tangent line there, and another slope of a tangent line here. You might have 3 of them. Because those are 3 different points, right? Oh yeah, and there's one up, oh, there might even be 1 or 2 up there. So you could have, for one x value, you could have like 3, 4, 5, 6 different tangent lines. Depends on what the curve does. That's why it's important that that derivative requires both the x and y coordinate. Every single one of these points has an x and a y, and an x and a y, and an x and a y. So I could go all day getting slopes of tangent lines. That's awesome. That's it. No, I'm kidding. We're not done. You've got the basic idea, right? You've got the basic idea? All right, so now I'm going to turn the screws a little bit. Let's see if you can handle this. Ready? That first problem, let's do that first problem. X squared plus y squared equals 16. A circle, radius 4. Find dx dy. Do you see the difference? It's reversed. What I'm saying is I want you to act as if y is independent and x depends on the y instead. Since you can't solve this for x and you can't solve it for y either way easily, then there's nothing that tells us we should have said, hey, y somehow depends on x. We could have easily said x depends on y, because neither one of them has the advantage in this, right? Do you see that? They're almost equally trapped. Yeah, let's see what happens. So I'm going to take the derivative now with respect to y of the left side, which again, I'm going to do a little shortcut. I am going to split it up into 2. I'm hoping that everyone here is comfortable with the idea that if you have a sum or a difference, you can split it, right? So I'm taking derivative of this and this and this, all with respect to y instead of x. Let's take care of the easy ones first. The right side.
The
Right. Zero. Okay, derivative of a constant is 0, and it always will be. The next easy one would be what? This one right here. Because y is down here, what's the derivative of y squared with respect to y? That's just 2y. Do you see how now that chain rule doesn't apply on that one because we're differentiating with respect to y? Got it? On this one, though, we're differentiating with respect to y, but x is the variable. So that's going to be chain rule. 2x times dx dy. And we have a plus between them. See that? And then we could go solve for dx dy and we'd be done.
How do you solve for dx dy?
Just move this to the other side. Divide by 2x. Yes?
Okay, yeah.
Okay. So you should get y over x. Negative y over x, thank you. Which is different from dy dx when we did it earlier. Wasn't it negative x over y? This one is going to be negative y over x. Because this is telling you how fast x is changing with respect to y instead of y with respect to x. That's kind of cool, huh?
How would you have notated that?
Exactly. That's the danger. Now, when you write y prime right now, do you see how this is not good notation? Because I'm assuming y depends on something, right? But I don't know what it depends on. The assumption is what? That it depends on x. And in fact, that's what we mean by this most of the time. Dy, dx. But without having any way of writing the x in here, it's not as clear as the Leibniz notation is. And if I were to switch it around, the only way to get this to flip over with the other notation with the prime is maybe to write x prime. And that maybe you could say, yeah, that depends on y. So this is dx dy.
That's assuming the other variable.
That's right. That's assuming the other variable is y. And that is what I'm about to do right now. You're going to see this. Watch. Okay? Find dy. Everything's good? dt.
What?
dy dt.
Same problem.
Of that.
Same problem?
Same problem.
That's not cool.
Okay, so think, what's that? It's going to be chain rule, but let's think about what's happening. In the previous two examples, we were saying, like in the first one, we said y depends on x, right? So as x changes, your y is being determined. Yeah? Or the way we did it right before this, we're saying if if y is changing, x is going to be determined from y. This is saying somehow y is changing with respect to t, but t doesn't even appear here, right? T does not appear in there? So what I'd like for you to think of is t as being, and the reason I use t is because I want you to think of it as time. So imagine that you have this circle, right? I'm going to draw it very lightly. But imagine that I'm drawing it, I'm starting, I don't know, somewhere, okay? And then I start the clock, and I start drawing this. Start drawing this circle. Start drawing it, right? And I'm drawing it at the same rate, like just going around nice, even rate. And that unit time is kind of this background variable that you don't see on the curve, right? You don't see it on the curve, but it's like this background thing that's happening. Yes? Then at any point right there, I was moving, right? And what I'm asking is how fast was the y coordinate changing with respect to that change in time? All right, well, let's see what happens. Let's just do it, okay? Let's just do it. I'm going to take the derivative with respect to time of the left side, which means I'm going to have two different derivatives. Like that, right? That's it. And We know that if these variables match, it's just the derivative the way we've been doing it.